So let's go and get started on chapter 13, concept preview. The exams are done, so you can get those at the end of the hour. But right off the bat, I think it would make sense just to call this a you do, and Google it, physics book, whatever. See what all those variables are. They're units, what they represent, and yeah. Let's jump to number 2. P is a function of R, right? So remember, that's how this is written. So get used to the notation. When you see notation in math, read it that way. It'll really, really help you. So when I say P is a function of R, right away, you should write something like this, right? It's really going to help you with all this stuff. And here's the equation. At what value of R is the function a maximum? How do we find maximum of function again? What do you do?
Oh, the first derivative.
First derivative, right? So I'd take d what then, Pablo? The derivative with respect to? R. Now, we didn't quite finish the story. You take the derivative with respect to R, but what are you supposed to set that equal to? 0. Yeah. Okay. So what's the rule for this? What is it called? Did you see R in 2 places?
Quotient.
Take the derivative of the first times the...
No, inside.
Take the derivative of the first times the second plus the derivative of the second times the first, right? Okay. So right off the bat, what can we do with this stuff? Do you see an R in it? No. So can we just multiply both sides by a naught cubed over 4z cubed and just get rid of the bloody thing? Pull it out of the derivative? Do it all in one big step? You comfortable with that? It's gone. You don't even care about it. It's gone. All right? So we're going to have derivative of the first times the second plus the derivative of the second times the first. Let's see. Well, maybe I don't want to do that, though. Oh, yeah, I do. It'll be a lot easier. Yeah, it will be a lot easier. Okay. So imagine that's not there. The derivative of here's your first. Right, here's your first. Here's your second. So the derivative of the first would be 2r times what? E to the negative 2r a naught plus derivative of the second. Ashley, would be what? So that's an r. See, it's an r. What is the derivative of the second? Yeah. How do you take the derivative of that? Right, it's an r.
Wouldn't it just stay the same?
Derivative of the exponential is the exponential. This thing's hard to write with, so you just got to forgive me for that. But it's the same, but you're not finished, though. How do you take the derivative? You're right, the derivative of e to the negative r, well, no, e to the positive r would be e to the r. But e to the negative r, yeah, you get e to the negative r, but you have to take the derivative of what's the exponential part. Then you'd have a negative sign out front, right? So this thing is really hard to use. I may have to go back to the old one.
When did you come out to?
So how do you take the derivative of this thing? How do you finish it?
don't think the A naught matters, does it?
Is it a constant?
No, because
Yeah,
of
that's a
R.
constant. Yeah, A naught's a constant.
What's the, let's do this. Look at this, this is crazy. This thing is just impossible. I think I'm done with this. If you take d dx of e to the negative ax, what would you get?
-A times E.
Negative a times
E to negative
e to the negative ax, right? So what you did is you just took everything. You don't care how complicated it is. Everything out in front of the x, you just put it out in front of the exponential. So what would you put out in front of the exponential?
-2
Over a naught, yeah. All right. That whole thing has to equal 0. So what could we do now? You could factor out the e to the negative 2r over a naught, or just,
And then you also got multiply times R squared, right?
oh, we forgot to multiply by r squared. Yeah, we forgot derivative of the second times our first. Huh? Thank you very much. That would have messed things up. Okay. So what can we do here? Can't we multiply both sides by e to the positive 2r over a naught? That would help. That'd really clean it up, wouldn't it? What would that look like then if we did that? Richie, what would that look like if we multiplied through by e to the positive 2r over a naught? Because I want to get rid of this. Why not? Might as well. Right? Because e to the negative x times e to the positive x is just, yeah. What do you get when you multiply those two together? You get e to the 0, which is 1. Okay, that's why I want to do it. So what would you get if you multiply through by e to the positive 2r over a naught? Multiply it times 0, you'd get 0. Okay, now the other side. What would you get?
2R.
Okay, we can just leave it all. Yeah?
-2 over A naught R squared.
Do you see how we went from there to there? No, Ashley? Multiply by e to the positive 2r over a naught. Both sides. Times 0, you get, take this times e to the positive 2r over a naught. You get 2r times e to the 0, which is 1. So we should probably write a 1 here, but take this times the same thing. All you're left with is the negative 2 over a naught r squared times 1. Okay. Solve for r. Can we multiply both sides by 1 over r? Is there anything wrong with doing that?
Multiply both sides by R.
By r, it's not going to help. 1 over r. That would help a lot, right? What would you get? What would you get then, Brad? What would you get if you multiply both sides by 1 over r?
2 minus 2 a naught r.
Well, what equals that though?
Oh, this is 0
0 equals.
equals 0 equals 2 minus 2 over a naught times r.
Yeah. So now we can solve for r. Bring the 2 over there. You have a negative 2. R is going to equal a naught. Okay. Okay. What is the symbol for the principal quantum number when describing atomic orbitals? We're talking about atomic orbitals for which atom? Hydrogen. All right. Little n. What could it be? Ashley, what could it be? You remember? No, periodic table is a big help, right? Remember, you could look at a periodic table and write the electron configuration of things. So what were the periods? 1, 2, 3, 4, 5, 6, 7. What were all those? You'd have like 1s, 2s, 3s.
Oh, the levels?
Yeah.
Sublevels?
But what little what? But what symbol? Q. Q is charge.
Oh.
It's little n. That's little n. 1, 2, 3, 4, 5, 6, 7. That's little n. Right? 1s, 2s, 3s, 4s, 5s, 2p, 3p, 4d. Right? So what could its possible numbers be? Well, yeah, according to that, 1 to 7, but maybe it goes farther, right? But I guess theoretically, it just keeps going. Can it be 0? Oh, yeah, look, it starts at 1. Okay. How about, Pablo, what is the symbol for the angular momentum quantum number when describing these?
L.
Little l. Remember, it was cursive, though.
Yeah.
Okay. There. Something like that. That looks better. And what are its possible values? Ricky, what could they be? L could be
Time.
Negative L to L.
well, no, the
Is it all real numbers?
the possible values. Yeah, let's see. Yeah, I was just thinking 0, 1, 2, 3, 4, 5, but you're right. It goes from 0 up to n minus 1. We might as well, that's the better way to describe it. See, I was just going to write 0, 1, 2, 3, keep going. But I think what Richie said is a good idea. Up to n minus 1, right? And the letters that correspond with each number. So, yeah, let's write them down. So you have 0, 1, 2, 3, 4, 5, and just keeps going. If L is 0, what was the little letter? It was S. If L is 1, man, Richie remembers this. These are small case letters. P,
Oh, S, T, D, and F.
D, F. What goes next? G, H, and then that's just alphabetical after that. I don't know why they do S. I don't know why they do SP. It has to be some conventional historical thing, because it's alphabetical after that. It just keeps going.
Sigma and E stand for pi.
Mm,
Wasn't it supposed to be like
no, then you're thinking of bonds. You're thinking of bonds. Okay.
Yeah.
That's fire.
How about so we have principal quantum number. We have principal. We have angular momentum. Now we want magnetic quantum number. Little m sub l. And what are its possible values? Negative L all the way up to positive L. God, this thing is ridiculous. Wow. Okay, negative L to positive L. So fill in the blanks in the below table. Only one value per box, and start with the value 1 and stop with the value 4. Okay. So our principal quantum number, right, that's our n's. Our allowed angular momentum quantum numbers are L's. Magnetic quantum numbers, m sub L's. And the number of orbitals. So just you have to count up the number of possible states you've got there. So n starts with what number? 1. Okay. And only one letter designation per box, please, for L. L goes from what to what? 0 all the way up to n minus 1. So what are the possible values for L?
0.
Just 0. There's not really much to write there. What could m sub L be?
From 0.
Yeah, that's it. Okay. So the total number of orbitals with the same quantum number is just 1, right? Because you just have one possibility here. So to have a different orbital, you need a different set of quantum numbers, different set of n, L, and m sub L. Okay? That would give you a different orbital. So we're not drawing pictures of these orbitals or anything. We're just trying to describe the possible quantum numbers that describe them. Okay, so the next quantum number, we're supposed to stop at 4. So after 1, you get 2. And what can L be? L goes from what to what? 0 and 1. See, I want to put it in different boxes. Okay? 0 and 1. So for L is 0, this would be 0, right? From negative L to positive L. If this is 1, this would be negative 1, 0, and 1. Okay. So how many states do we have here? We have 1. How many do we have here? We have 3. Yeah. 1, 2, 3. So you have 2, 1, negative 1. That's one state. 2, 1, 0, another orbital. 2, 1, 1, there's another orbital. So you end up with 3 total. Okay. So then the next one would be 3. Yeah, so just fill us out for 3, and then we'll see if we agree. Yeah. And then just keep going. Okay. So before, you can do the number 4 at home. That can be a you do. But I want you to notice something. This is for n equals 1. Here's for n equals 2. Here's for n equals 3. Okay. Oh, we're supposed to put the total number of orbitals with the same quantum number. We didn't answer this. Oh, that's true, I guess. So for n equals 3,
So did we answer those right, though?
we're right so far. So if n equals 3, what's the total number of quantum numbers?
If n equals 3.
Sorry, what's the total number of orbitals? If n equals 3, you'd have 9.
Oh, of everything?
Yeah. When n equals 2, you'd have 4. When n equals 1, you just have 1. So what's the relationship between, well, just we haven't gone this far, but the total number of orbitals and the principal quantum number?
N
Times 2 would be, this would have to be a 6.
N to the
It has to be n squared. It have to be n squared. Okay. So you can finish up this one. So n equals 4, you better end up with how many orbitals? 16. Angular momentum is described by big L. Show that L and H bar have the same units. Okay, you should have a good shot at this. Try it. What's M?
Mass.
Mass. So no, it's
in kilograms.
in kilograms. V,
I'm assuming this is this V or?
that's V. Their nu is nu. That's a V.
Velocity.
Nu is
So that'd be
that
meters
big
per
thing,
second.
meters per second. And R should be in,
Radius will be in meters.
yep. So figure out what those standard metric units are. H bar, see what its standard metric units are. They should work out to be the same thing. So Planck's constant has units of angular momentum, if you can show it. That should help. And if I put
Wait, for H bar, that says joules second. That's supposed to be joules over second? That's what I always thought, but...
Yeah, so that's kilograms per meter.
yeah, put in what a joule is, and
Yeah, kilogram per meter squared per second squared.
I just remember joule is work, which is force times distance, which is a Newton meter.
Yeah.
And then a Newton is F equals ma. So that's how I do it. Otherwise, I can't remember all those stuff.
What was your trick again?
My trick for a joule is I just remembered work. That's work. And work is force times distance. And I know that force is newtons, which is mass times acceleration. So work is mad, right? MAD.
Oh, I see it now.
So it should work out. So Planck's constant has units, the same units as angular momentum. So so it's kind of a insight into nature there. So then, did you get it? You didn't get it to work?
For the L, the angular momentum, if you cross out the meters, because they both cancel out.
Mm-hmm.
And I stuck at kilograms per second.
We should end up with the same units on both sides.
Well, I thought you multiply the meters.
No, because
Yeah, you do, because that's F over 1.
Well, so you saw where you're messed up?
So you do get the same, I think.
Yeah,
Acceleration is meters per second squared.
yeah, you should get the same on both sides.
Oh, seconds squared?
Should be.
You just get seconds.
yeah, it's meters squared.
No, what?
Speed is per second.
Yeah.
Meters per
Acceleration is per second squared.
Yeah.
Because I have kilograms meters squared over
See?
seconds.
No, that's not what you
distance is just meters.
And distance,
So it would be
meters. Kilogram meters squares
Oh, okay, so
over
second
second
square.
squares.
So
And then,
second
because it's a
times
joule second.
Oh,
So
okay.
that's why you left it this. When you do,
Okay, I see that.
okay. Yeah.
can't get the square on the second. What?
You're not supposed to.
Oh, I'm not supposed to.
No.
I know.
So then,
Because
No.
H
no.
bar it goes joules
Okay.
times seconds.
Go to the one.
So joules is kilograms, meters, seconds over meters squared over second squared.
yeah.
And since it's times seconds, the seconds cancels out, so you only have 1 second on the bottom, which is equal to because I'm assuming you got kilograms, meters squared over seconds. Yeah. H bar is joules times seconds. So
Okay.
Yeah, joules times
We're
second.
doing electronic
Alright.
configuration.
And it's
I got it.
MAB. And then from that,
cool.
Okay. So you got it?
Yeah.
So we need to practice using
That's the whole configuration, right? That's not the short version.
the whole thing. Okay. So you ready? So we need to practice using this diagram to get ground state electron configurations using these solutions to the Schrödinger equation for the hydrogen atom, right? 1s, 2s, all that sort of stuff.
Yeah.
So what we're going to do is usually, this thing works, but this is a lot better. So the ground state electron configuration of silicon. Okay, so you'd start out silicon, right? And where's silicon is what number? 14. Okay, so it's way in here somewhere. And you notice where things start getting messed up and weird is zoomed up in this box, right? That usually you'd say 3D. Notice how 3D is lower than 4S. So usually you'd be saying you'd be filling 3D before 4S. But notice where they zoomed up, that's not the case all the time, right? So we just got to be careful and follow the chart. So if you're doing silicon, right, 1S, you'd fill the 1S, 2S, and then the 2P, then the 3S, then the 3P, then the 3D, then the 4P, and that's keep going. So we don't need that many, but you fill in 14 electrons. So you'd have 1S. How many can S take? 2. What's next, according to the chart? 2S2. Then you'd have 2P6. Good. All right. 8, 10, 12. Yep. Okay. So an excited state electronic configuration of silicon. Okay, I guess they're talking about the first excited state. So we could have kept writing here. If we would have wrote the next orbital, what would we have written? What's after 3p? According to this chart, what's after 3p? 3d. Okay. So, and we should write what number up there? 0. And you could keep going, right? But if we're only interested, pretty much all of these, we're only interested in the first excited state. So we're just going to jump up into the next orbital. And it's a first excited state. So what's the minimum jump that you could make?
3D?
Jump into the 3D for sure, but jump from where?
3P2?
The 3p2, because that's the closest one to it. So your first excited state would be the exact same thing, except at the end you'd have 3p1 and 3d1. Okay. And then all this other stuff would be the same.
Cool. Oh, okay.
Okay. So you can go ahead and do the same thing for all these. See if you can wrap this up. Then you won't have a whole lot for homework.
Cool. And when you go we base it off the little chart you
Yeah, and everything's based off of this.
Vanadium is no, I'm just kidding.
It's B, right?
Yeah,
Okay.
23. See it?
And we'll give much more background information on this when we start the class. It's just I just wanted you to learn how to do this.
Yeah, this stuff's pretty interesting. Do they put this stuff on the PCAT? 'Cause I know they put it on the MCAT, right?
I don't know. Things have changed since I've.
Yeah, now they're coming out with the new MCAT in like 2016.
Be new and revolutionary.
Yeah, like Windows 8, more difficult and doesn't really do much more.
No.
Windows 8 is horrible.
It means desktop.
Just make more frustrated doctors.
Separate from artifact. There must be something to do with your electronic device.
Is it D that holds 10?
Yeah.
How many does F hold? Like
14.
14?
Yeah.
Just gotta throw some G's on it.
Yeah, whatever you don't get done here is homework, so might as well do it now. Now notice this was kind of a. Is there more?
Yeah.
There's more?
Oh, after that?
No, that's it.
There's just one more page, but that's not bad.
So this is, notice how this is a pretty short concept preview. This is your last one. So from last upcoming chapters, there isn't a concept preview
Oh.
to give you a heads up. So things are going to feel like they're going to be accelerating because we don't need it.
Oh, well,
Notice how this is already getting smaller and smaller.
I just read that awesome already.
Yeah.
What is it like? What is it like?
So the-
Applications and
It's
stuff? Or what?
it's nothing that's that bad.
So you're saying
That hasn't been covered or really previously. I don't know if it's easier, but you don't.
Vanadium?
The purpose of the concept preview is to review math or physics concepts that I don't want to be hurdles to the homework.
Oh, okay.
Sorry.
That's the only purpose of this.
Oh, okay.
No, I screwed up.
so there are no hurdles
It
on
should
it.
be
I don't think so.
3d6,
That's just
3d5.
How many for excited states?
Because it can't be 3v3 because it's not.
Do I follow the whole? Because I'm thinking of it right now.
Yeah.
For excited state for
Uh,
V.
'cause that's
Am I always
Isaac
moving one
though with
electron?
the
Because I know
electrons that
the D levels usually like to be half
Can't.
filled at least.
Yeah.
If it's-
Now realize, for what we're doing here, for these purposes, we can write an infinite number of excited states. Now whether that transition occurs or not, that's selection rules, and that's conservation of angular momentum, and all these sorts of things get in the way. So we're just writing states right here.
So
We're
how many
not.
electrons am I moving to my D level?
You're just moving one, right? Because the total has to stay 14.
I know, but for my P level, for V. Because I have 3D5.
Well, you just move one electron all the time.
Oh, okay.
Just move one electron. Now you could move more than one, but that's not the first excited state. The thing that's missing here is it should say first excited state,
Oh, okay.
because this is the minimum.
Okay.
Because otherwise, you could write anything,
Yeah, that's all-
and I
that's all-
can't,
that's all
as
fine.
long as you had 14 electrons.
Okay.
Otherwise, you ionized it.
So I can just make stuff up. No, I'm just kidding. I was gonna ask you, can one electron jump, like let's say from 3D to 4S, and then another one jump
Okay, now
from
hang on.
3D to
Now, We're just writing excited states. We're not writing allowed excited states, allowed transitions. We're not talking about that yet.
Oh, I was just
So
curious.
this is just practicing. So no, you can't go from certain orbitals to certain orbitals, and that's called selection rules, and we'll get into that.
Oh,
Vanadium?
Okay, so for the
Yes, sir.
excited state for D,
Mm-hmm.
because it's at
I'll tell you.
3D3, because the graph is 3D, and then it goes to 4s2. So what would the
Wouldn't you have 3D5, right, for the ground state?
Yeah.
You have 3D5 for the ground state. So that's going to become 3D4, and then what's next? 4S1, right? Isn't that the next one for vanadium?
vanadium is 3D3 4s2.
3D3. Why did you stop? No.
You're supposed to follow the little graph. Not what we're talking
What's
about
the?
here.
No, because it's 3P6, and then it's
No, I was gonna say you're supposed to follow the graph.
And then you go 4x.
No, you're supposed to follow the graph.
Gotta follow the graph.
Instead of what we know, we're supposed to follow the graph.
I mean, what do you mean with this graph?
You see how the graph goes 3D, then it goes 4S? Like it goes 3P, 3D.
I don't understand this graph.
You just follow the lines pretty much. Which is the next one from 3P?
It's good, there's a lot of lines.
3P is 3D.
yeah.
Alright, you got it.
You write them on the side.
So on that last
Write 'em
one,
on the
sir,
side, right?
So then from 3P,
Well, it's actually
would that be,
All right. For vanadium, you should have all that stuff,
it should be all the way up to,
right? For vanadium, 3D5, excited state.
3D4,
Yep.
and then 4S1.
Perfect.
So I'm talking about that calcium.
3D5,
Yeah.
Yeah.
It should go all the way up to 4S2,
Yep.
the ground state. And for the excited state, would it be 4S1, and then it would go to 3D?
1.
Oh wait, what'd you say?
The ground state goes up to 4S2, and then the excited state goes to 4S1 and then 3D1.
Wait, what? So you do have to do it that way.
Well, Dr. Smith, is 4F before 5P?
Depends on which.
Because this graph looks like it's like the same area.
They crisscross.
Yeah.
Depends on where you're at. Look, see how it depends on what your Z is. What's Z?
The number of electrons?
Well, technically Z is the atomic number.
Oh,
The atomic number is the same as the number of electrons, though,
okay.
right?
So Z atomic number.
So whether you fill the 4F before the 5P, all depends on the atomic number. So you have to use this chart and learn how to, right?
so then from 3P,
Now, am I asking you to follow the periodic table? Focus should be up here, right? Follow your atomic number, and then you just go straight up, and that tells you the order.
That doesn't make sense if you're gonna have 23 here and then 4S. But when you have 24, it's all right. You see what I'm saying?
3D5.
So the only place where you can tell by eye what to fill the order everywhere except for where it gets really zoomed up, and that's where they blew it up for you. Otherwise, you just follow the order that you see.
Yeah, those are all the atomic orbitals. So you're gonna fill the ones that are lower.
And it's even right here too.
What, that says 4?
See how we're between 1 and 25 right now? Like the first one was
Where are you getting 25 at?
oh, I was just saying, I was just picking like an arbitrary little range right here.
Oh, okay.
All of our
Yeah, no,
atoms that were interested, silicon
Right
is how
here
many?
you did, even goes 23.
Where?
in 3s.
Which one are you trying to fill?
This one. So you're saying my
For vanadium?
Yeah.
Well, just look at how many electrons does vanadium have? 23.
Yeah.
So you pretty much find 20 and just follow this order.
Okay.
And then where you can't really tell by eye anymore, that's why they zoomed it up.
Okay.
So for it'd be 1s, 2s, 2p, 3s, 3p, right? And for vanadium, see that red line is below it, so it'd be 3d. And then the green one, 4s. So you have to be going across from this one.
Okay.
Hey, Smith, is there a way that, I guess, can you, like, put that on a Word document for us so we can print it out?
You have it in your notes.
So we can get, like, we can enlarge it. Well, I want to enlarge it so I can see it better.
And then
I just have to print it out.
Well, the
But what was it?
you
Oh, is this
Or is it like in the
3D?
book or
And this
something,
is
or-
3D?
where do you have trouble seeing it?
And then 4s.
because in the book it's not as defined as
3D.
Yeah, like, that's in color, so.
Yeah, it's in color.
Yeah.
It's like in black and white.
Oh, well, you have to use your
I think
textbook
it
then,
holds 10.
probably.
10?
Uh-huh.
Alright, so then for the excited state, I'm going to 4.
Which one are you talking about?
Vanadium.
Vanadium. So vanadium, the order is the red one, 3D, and then it's 4s, and then it's 4p.
So I would go to 4 as excited.
Yeah.
Mm-hmm. If 3D is your last, if 3D is your ground state, yeah.
Okay.
3s2, 3p6, 3d2.
Uh-huh. That's for the ground state, yeah.
Okay, now calcium is 20.
3s, it would be 3d1.
So
So you gotta follow that order all the way up until where it gets confusing. You see calcium up there, and see calcium. It's filling that green one before the red one,
Oh,
Make sure
okay.
you write 3D1 and then 4S1.
because it's really hard to see. So that's why you have to use the blown up part.
That's why I
Okay.
use that because you can't see in the book.
So you need to get used to using the black and white one, because that's what you're given on the exam.
Okay.
So, but once you figure it out, it's not so hard.
Yeah, it's just, yeah, it's better to use it.
Yeah, I think I got
So
it.
it's gonna be 4s2.
So I can't bring in my own blown out color copy.
Yeah. So you want to stop at what number?
For the whole
23?
class.
See, look at that. This is nice because you can see this.
Right.
Look at this. It's like, look at that line. It's like, oh, that's a line.
Yeah, but you can tell what that is.
But yeah, now that I look at your nice, perfect one.
Yeah, you can tell what it is. Just write a 4S on
Yeah,
that.
now that I have a nice
It's pretty.
comparison here.
It's pretty clear.
Yeah, with this comparison,
Yeah.
it's pretty clear.
That's true. Once you know what you're looking at, it's a lot easier.